All right, our last video, our last bit of material, we can do it. So for solving exponential and log equations, the thing is we need a way to, well, solve for x. The problem is x is trapped in an exponent. So I want you to hear this. Is there any way, anything we could do to both sides that would allow us to drop the variable from the exponent down onto the, I guess what I'm going to call regular level of all the rest of the numbers? And the answer is you introduce a log. So just to say, and we're going to approach this in two ways. Now I'm going to show you this way once, and it goes through the rest of them. Um, I might use it a few other times depending on if I don't quote unquote like the numbers, and you'll see what I mean. But for this one, really, I hope we could answer this without logs. I hope we could just say, oh, 3 squared is 9, and I'm done. But yes, but what do we do when the numbers aren't as easy to recognize? Or what if they don't actually, what if your answer isn't a perfect power? What if you need to get something like log of 14 over log of 3 or whatever? How do you actually get there? So here's the approach. Again, don't miss that the answer is just 2, because we know what 3 squared is. It is 9. But the mathematician way we're going to solve this now is saying, I can introduce a log to both sides. Now, it doesn't matter what log I introduce. Now, in other words, I could say that I want this to be log of base 3. I could say I want this to be ln. You could try it both ways and see that it'll work, or you could try it anyway, because you could also actually say you want log subscript 17. Now, why would you choose that number? You shouldn't, but I'm just saying it actually doesn't matter what number you choose as your base, just as long as you introduce the same log on both sides. Why? What are we going to do? Well, we're going to use the property of logs that says an exponent in a log is really just multiplying out front. And that was what I was saying at the beginning, is I've now found a way to free my variable and put it on the same level. And my last step then would be to divide the log of 3. Now the thing about that is, there's two ways of writing that. Either like this or like this. And what I'm kind of highlighting here, sorry, make sure the 9 looks like a 9 in there. What I'm highlighting here is, again, just the two different ways you can type things in your calculator. I can either type just, well, even just to prove it, I could type in ln of 9 divided by ln of 3. I still get 2. I could type log of 9 divided by log of 3, which gets me 2. I could type in the actual, you know, once they're dividing, it looks like this. That still gets me 2. I could even go crazy, like I said, and I could say, what if I wanted the log of base 17? Don't do this. This is just to show off and be fancy and show you that it's possible. That still ends up being 2. For crazy math reasons we don't have time to really get into, but essentially just know, the bigger thing I want to highlight is if you have two logs dividing, it's the same as writing it in this format. This actually is a formula called the change of base rule. The reason it's called change of base is because this is rewriting these two separate logs that are technically in base 10 to writing a single log in base 3, if you kind of catch that wording there. So that's why it's called change of base. These were two separate logs written invisibly with base 10, and I now was able to write them as a single log in base 3, which makes sense because 3 was clearly my base. Now, finally, the very last connection point we need to make here is, don't forget we learned about log is bay, and so what I'm going to do now is really speed run this problem and say, hey, if I remember that there's a base, an exponent, and an answer, then Mr. Rao taught me that I could rewrite that as log with base, the answer, and it gives me the exponent. But here's what we just did. We proved why that formula works so long ago. So don't miss that wording. How did you actually get here? Because you applied a log to both sides. Your property said the x could drop down. You then needed to divide, and dividing two logs is the equivalent of writing them in a new base of the bottom log. And guess what? It loops all the way back. It's just one giant circle now, which is kind of crazy. But of course, we need the actual answer. The answer is 2, which in this case we knew long, long ago. Okay, let's continue. And now I want to show you some interesting things your homework does. Your homework starts to kind of challenge you less on applying the log to both sides and more on can you identify a common base between numbers? Or in other words, hey, I see a base of 8. Is 512 some power of 8? Is it 8 squared? Hopefully we know it's not 8 squared because we know that's 64, but is it 8 cubed? And already the answer is yes. Now watch this, because this is an argument you'll see on your homework for the help me solve this. They'll say instead, oh, 512, that's just 8 cubed. Now I want you to think about the problem like this. This is not anything that actually requires a logarithm. It's saying, hey, if I have this 8 to a power and 8 to a power, then really I just need the powers to be equal. Or in other words, what this question's really asking is, when is 2x minus 11 gonna be equal to 3? And now, hopefully you see the power of writing them as a similar base. Now, we don't even need logs to solve this, although we could use them. Now I just add 11 and get 14, and I divide by 2 and I get 7. I am doing that all in one step, but all I did was add the 11 and then divide by 2, and it gave me 7. Um, I think it's worth doing this example the way I showed you a second ago. Actually, no, I'm not going to, because I'm going to trust that you could do it and try it. I'm going to instead do this next example the way I did the first one. Because this time I can just go ahead and tell you 128 is larger than 32, so actually both of these bases would need to change. Um, and in fact, I think the most similar base I could use for each of these is 2. So you'd really have to go back and say 2 to what power is 128. And now, sorry, I gotta make sure. 1 minute. For a minute, I was freaking out that 128 wasn't a power of 2, but it is. Anyways, in that 32 is also can be written as a power of 2. Rather than do that, I think in this case it would be most advantageous to just say, let's just take the log of both sides. Makes it pretty easy to type in your calculator. Now, also, again, I am going to say you could just do your log as Bay formula and be done, but let's show again why that formula works, because I think that's pretty fun. So we log both sides. The x can now drop down because it's the power of a log. I can then divide the log of 128, or in other words, I can rewrite it as the change of base formula. That's what I'm going to jump to. Because 128 would divide and be on the bottom, I can now write this as subscript 128, and I ultimately wanted 32 originally. Now this, again, I need to solve it, so sorry, I shouldn't put a box around it, but this, the reason I put a box around it is your log is base formula. Because there's a base, exponent, and answer, it gets rewritten as log of your base, your answer, and it gives you your exponent. Now, in other words, that means I just lastly need to go to my calculator and say, what is log of, 32 divided by log of 128? And I get this ugly fraction. Every calculator somewhere has a math fraction button, and so I'm going to click that button, and now I get 5/7. 5/7. Okay. This one, I guess because it's a nice simple example, I will show you the other way around for this example super quick. In fact, I can do it over here. The other way to write that is by saying, oh, 128, if you actually work it out, is 2 to the 7th power. All right. And then 32 ends up actually being 2 to the 5th power. And so you can already see where your 5/7 are coming from, sort of. The one thing is this is 2 to the 7th to the x. And what happens when I have a power to a power? And I think we saw this before, but they end up multiplying. It's a rule of exponents. So now what happens? I've got 2 to the 7x, I've got 2 to the 5th. I want to know when those are equal. Well, because they have the same base, I'm just asking what are the exponents equal? And the answer is 5/7. So that's the last time I'm going to show both versions in one. Up next, through the rest of these, I'm just going to choose. um, because I think it'll just go by faster. And I don't want to confuse you. Sorry if it has been confusing that we've done each one slightly differently. Hopefully what you see maybe on a second watch is just really it's the connection of everything in this chapter all coming together, all showing us different ways of saying the same expression. Now that's confusing because we like to say, oh, math can only be done one way. But with logarithms, you can see you can kind of have some freedom and choice with how you want to approach the way you're arriving at a solution. Now the reason also, sorry, last thing, and then we'll just cut through running through examples. The last thing to say there is why would I not just use logs? And it's because I can identify outright that well 3 and 9 go together. That's why my answer comes out nice. 8 and 512, I knew that those were related in their powers. 128 and 32, I knew that those could be all the way written down back to a base 2 because I recognized those numbers because they're your iPhone battery size or memory sizes, or at least they used to be. I think now we start at 64. But you get the point. I'm looking ahead and saying, oh, wow, because these numbers can be easily rewritten with a usable base or they're not too wacky of numbers, quote unquote, that depends on your comfort level, then I don't need logs. However, I think we should learn now, let's just use logs, because after all, why did we study this whole unit? Okay, so again, 4 and 16, they're related somehow. Hopefully you know the exponent that turns 4 into 1/16th, but I'm not going to determine that. And in fact, what I'm going to do here in number 4 is I'm not even going to introduce the log on both sides. I'm just going to utilize and exploit my log as bay formula. And I'm going to say there's a base, an exponent, that's two things, and an answer. Well, then I can write this as a log with a base, answers on the inside of the log, and now the exponent is on the other side. So here's just that log as bay formula. Base, exponent, answer, base, answer, exponent, log, bay. So from there, now that we've done that, this is where you jump to your calculator and type it in. For sake of time, I'm not going to do that anymore because I trust you can, and that ends up being -2. Or again, maybe from what I said earlier, you identified that. Now I just need to solve this. What I'm going to do to solve this is I'm going to double swap. I'm going to add the x to this side to make it positive, and then I'm going to add the 2 to this side to get the x I just moved by itself. So those two moves real quick just means you will end up with x equals 3 for your final answer. Okay, so now we're moving a little bit more quickly. Up next, first thing I need to do here, well, oh man, I keep saying I'm going to stick with log as bay, but this one really, I'm not. Here's why. Now you know this isn't pre-watched and pre-worked out. Because I know what a square root is. It's a 1/2 power. And look at this. It's so convenient because it is 2 to the something, should be 2 to the something. And so that means, oh, I already wrote this literally as the same base. Then I don't even need to worry about that base of 2. I just want to know where these fraction exponents are equal to one another. And even so, this, what I just did from here to here, it's about to happen again because, yes, I do have ugly fractions, but even those fractions have the same denominator. So guess what? I actually really just need the numerators to be equal. So again, hopefully you're following that. Because it's the same base, I just need those exponents equal to one another. Or sorry, yeah, those exponents, which are fractions, equal to one another. Now that I'm looking for where those two fractions are equal to one another, because they have the same denominator, I don't need to worry about that. I just need to say when will my numerators be equal? And the answer is when x is 8. So, sorry, that one really didn't lend itself to introducing logs everywhere because we still would have had the fraction to deal with. This one was just special because they literally had the same base. Okay. Now though, I'm gonna break and continue back to log as bay. So, I have a base, an exponent, and an answer on the other side. So I can rewrite this as a log of my base, my answer on the other side. Goodness, we're gonna have to type square roots into our logs. And that should give me the exponent. Now, you need to type that in carefully, but you still can type that in. We haven't really dealt with typing roots into our logs, so I'll do that with you. But this will be first, it's the top one. So 1 divided by, where's my square root symbol? 1 divided by square root 5. and that's all divided by the log of 625, and I get negative 0.125. If I find my math fraction button, that's negative 1/8. Here we go. And if you're wondering where does that come from, um, well, remember that because this is a square root, there's a 1/2. Because it's on the bottom, there's a negative, and 625 is the fourth power. And all I'm going to say there is, if you kind of think about the numbers, a 1/2 and a 4, but one was on the bottom, one was on top, somehow they had to go together. The 1/2 and 4 make the 1/8, and the negative comes from the fact that it was on the bottom. Interesting. I'm not expecting you to get that from memory. I'm just kind of saying, how can you relate your answer to what you see on the page? And honestly, you don't have to. You can just type it into the calculator, get the answer, and move on. All right. Up next, again, we've got a scenario here where we could make equal powers, and we might need to because, after all, these, if I take the log of both sides, I still have variables on both sides. Now, the other thing I can do here, catch this, is I could instead introduce the log of a common base. What I mean by that is, now instead of just saying I want to log both sides, I'm going to say I want to log base 5 both sides. And I'm even going to go this step of writing it like this. Now, this is coming from, with time and practice, I know that 25 and 625 are all different powers of 5. And so notice the way I'm writing this, what I'm doing is I'm saying, I'm intentionally going to write this with a base 5 log. I already dropped down the used to be exponents. And now I'm going to solve these two questions themselves with my log properties. 5 to what power is 25? Or again, just type in your calculator. Again, don't miss that. You can just use your calculator. I think that's the hardest thing of teaching this section, if I could rant, is that I'm trying to always remind you that some of it is mentally done and some of it requires the calculator. But 5 to what power is 25? The answer is 2. So really, there's a 2 multiplying that whole expression. I'm going to rewrite it by putting that out front. 2 multiplying to that whole expression, because that's what log 525 is. It's 2. Similarly, and I already said it in the last example, log of base 5, 625 is 4. Or in other words, 5 to the 4th power gets you 625. All right, now we're just solving these. That's 2x plus 16 equals 4x minus 16. And I am just, sorry, for the sake of time and space, going to cut to the answer. I'm going to subtract, and that'd be 2x. I'm going to add, that'd be 32. And then I would have to divide, and I believe I would get 16. And now I'm going to double check. All right, and I did turn out to be correct. Okay, as we go through the next ones, now here's where we definitely need logs, and we need logs in kind of log as bay itself, because 5 and 23, I just already know those aren't compatible, so to speak. So this is where I'm going to directly say there's a base, an exponent, and an answer, and so I can rewrite this as a log of this base. I want 23, and I need to know what the exponent is on the other side. So log is base, answer that used to be on the other side, BA, and then equals the exponent I was looking for, x. Now this one, when you do your homework, you're literally just going to have to, they first want you to write the precise answer, and then they'll just want you to round it to 3 places. Again, don't forget that if you don't have that little subscript, that these logs are really just 23 divided by, and we get 1.948. Great. Let's keep going. Similar things going on here. First, actually, I haven't actually isolated the base here. So my first step here is actually just dividing the 7. Now, I don't actually know what that is, and guess what? I don't need to, because I'm ready now for introducing a log. There's a base an exponent, and an answer. So I can work this out later. And what I'm going to do is, because this is e, hopefully you know what I'm going to do. I'm going to introduce ln to both sides instead, or rather I'm going to log as bay this with ln, because there now is a, let's see here, a base of e, or you know what, sorry, maybe I'm jumping ahead. Let's write it like normal, and then we'll say why the ln pops up. There's a log with a base of e. I want 113 over 7, and I need to get the exponent that gives me that answer. Now, here's where the ln comes from, is what I told you is, if you ever have e as a base, you actually just come up with a new way of writing it. And that's nice, because that means literally now I'm just going to my calculator. Now catch this. I'm going to my calculator and I'm saying, what is 113 divided by 7, all inside of that ln, because all of that was my answer. That's now inside my log. So there we go. All right. Now, one last thing to say is the other way you could write that, just to say out loud, is you could write ln of 113, if you learned your rules, ln minus 7, because those were dividing in a log, and dividing in a log is subtraction of two logs, and look, same answer. Crazy. All right, let's really move. So we need to introduce log as bay. That one can be done pretty easily because it's just a single base, single exponent with some terms. Answer on the other side. So base answer equals exponent. Now, careful how you write this, but that means your answer is going to be precisely, sure you wrap that in parentheses maybe, and then just minus 1 to the other side. So, whoops, or yeah, you can still see that. So the first time, literally, you just write in the precise answer. You don't actually work out what the log is. And then in the second box is where you actually type this in around it. So because that exponent was x plus 1, we just get our log, and then we subtract 1 afterwards. Okay, we're doing really good, but now we're going in reverse. So now this is just log as bay in reverse. Catch this. So e is my base, the answer is x, and the exponent, because this is now in log form, this is BAE. There's a base, there's an answer, there's an exponent. Let's rewrite it. That must mean e to the sixth is x, and there I'm actually just done because I just solved for x. So that log as bay formula is really, really powerful. Base, answer, exponent, exponent, sorry, base gets an exponent and tells you the answer. And there was no work to do there. Now, it won't always be that simple, but thankfully there's not too much more to do here. So now what I have is, due to log as bay, I've got a base, an answer, and an exponent. So I'm going to rewrite it as base, my exponent, and my answer. But you can see, even so, this isn't going to be too much more work, but I can actually identify what 2 to the 4th is. 2 to the 4th is just 16. And I can subtract the 3 and get 13. Awesome. We're so close. All right. Now, what we haven't seen is we haven't seen two logs at one time in one problem. But here's the short answer. We don't need two logs in one problem. So because these are two logs that are adding, guess what? It's one log where the contents are multiplying. And now that I've got one log where it's a base, an answer, and an exponent, I can rewrite that as my base to the exponent is my answer. Now, careful, watch how I write this. All of this was in a log and it was multiplying, but now I'm going to write that as 2x squared minus x. I'm going to distribute that x as I rewrite it in this new form. Okay, well, what do I do with that? Well, bummer. This is 3 to the first, which is just 3. There's an x squared to my problem. There's only one way to solve things with x squared. You're going to have to move it over to one side and either factor or use the quadratic formula. I'm pretty sure this is going to end up factoring, and I'm going to do that by what I call just guessing and checking. We talked about this before in the very beginning. So now we've looped all the way back around to factoring. I think there's probably a way to write 2x squared as 2x and x. I mean, that's the only way. And it's either 1 and 3 or 3 and 1. I think I can already see. No, I think I can see that the 3 goes here and the 1 goes here. Now, because I'm subtracting to make 1 in the middle, I need one of these to be positive and one to be negative. And so if I think about my foiling, again, that's the only way to make 2x squared. I could have put 1 and 3 or 3 and 1, but I did some pre-thinking. And then I need a negative 1 in the middle. So here's positive, or here would be 2x. Here would be 3x. If I want to make a negative 1 out of 2x and 3x, then the 3x needs to be negative when they multiply, and the 2x needs to be positive when they multiply. And last but not least, where do each of these equal 0? Well, you set each one equal to 0. And if I add 3 and divide 2, that's literally 3 over 2. And if I just subtract 1, I've found my other answer. And congratulations, you've just finished your last lecture in college algebra. It's been a great semester. Good luck. Let me know if you need anything.